Good morning, everyone. I'm Sarithakumari, working assistant professor, working in Aeronautical Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today, my topic is calculation of resistance for solid conductors and inductance of single phase transmission line. That means a single conductor. So the course outcome from this for this is. Uh, the transmission line parameters of single phase and three phase transmission line using the concepts of GMR and GMD calculation. So basically the transmission line, we know that transmission line means it is a conductor to transmit the electrical power power from one place to another place. So basically that is the thing. A transmission line means a conductor. So here the transmission line conductor which is placed on the supporting structure, right? So which is placed on the supporting tower with a insulator. So the transmission conductor is placed on the insulator on the transmission tower. So because of that, the current in the conductor is confined only to the conductor. So that is what happens by providing the insulator. So now the transmission line parameters. Here there are four transmission line parameters. Um, so resistance, inductance, capacitance, and shunt conductance. So these are the various parameters which comes into picture when a conductor is carrying the current, that is in case of transmission lines. Resistance, inductance, capacitance, shunt conductance. First about resistance. So here the resistance is always exist in series, and this resistance is important in transmission efficiency evaluation and in economic studies. So because that means we know that because of the resistance there is always some power loss. So that's why it mainly affect the efficiency of the transmission line. Next, the next the transmission capacity is mainly governed by the inductance. It is governed by the inductance also. That is also exist in series. So that is how the inductance affects the transmission line operation. Next, capacitance. The capacitance is always comes in parallel. That means shunt. So it comes in parallel in the transmission line. That means that may be between the two lines or between the line and the ground. So here the shunt capacitance causes a charging current. So I'm talking about the fourth point. So the shunt capacitance causes a charging current to flow in the line and is assumed importance in medium and long lines. So it mainly this capacitance causes charging current to flow in the line. So that is different from the actual current, right? So and what it does we'll see later. So and this shunt capacitance effect is mainly important in the medium transmission line and long transmission lines. What are these also we'll see later. Medium transmission lines, long lines. Next, last point, the shunt conductance accounts for leakage currents flowing across the insulators. So that is how the conductance present in the transmission line. So mainly this accounts for leakage currents, okay, which flows through the insulators and also through ionized path. Okay, so ionized paths in the air. So this happens mainly the cases when the lightning occurs during thunderstorm conditions. When lightning occurs, okay, we have this ionized pathways in the air. So that is how the shunt conductance comes into picture. Next, uh, first about the resistance. Uh, the resistance, we see about the resistance of transmission line. The DC resistance of a solid round conductor, that means when the flowing current is DC, then the resistance is given by, this is a basic expression in terms of resistivity. Okay, so this is a DC resistance expression is equal to rho L by A. Rho L by A, where rho is the resistivity of conductor and L is the length of conductor, A is the cross sectional area of conductor. Okay, next, effective AC resistance. So AC resistance, when current flowing in the conductor is AC, the resistance is given by, the resistance is calculated using this expression, that is given by average power loss in conductor in watts over I square. Okay, power loss over square of the current. That is how generally AC resistance, okay, effective AC resistance they call, it is calculated. Okay, and it is in ohms. Now, this conductor resistance mainly affected by the three factors. They are spiraling, temperature, frequency. Okay, spiraling, temperature, frequency. So these are the three things. Spiraling means the if the conductor is in the form of a coil. Okay, so that factor also affects the resistance. So spiraling, okay, number of turns. Coil is in the form of a turn, a coil. Spiraling and temperature and frequency. So these are the three things which affects the resistance. Next, calculation of resistance for solid conductors, because we know that resistance changes with temperature. So if temperature increases, the resistance also increases. And here, look at the second point. For small change in temperature, the resistance increases linearly, and the resistance at temperature capital T is given by, okay, so suppose we want to know the resistance at a temperature, particular temperature capital T, then that is given by RT, which is R suffix T, which is given by R naught into 1 plus alpha naught capital T. Okay, where RT is the resistance at T degree Celsius, capital T. R naught is the resistance at 0 degree Celsius, and alpha naught is the temperature coefficient of resistance at 0 degree Celsius. So this is a expression for resistance at a temperature capital T. Now, by using the above expression, the resistance R2 at temperature T2, capital T2, can be found if the resistance R1 at temperature T1, capital T1, is known. That is, from this above expression, okay, R2 is given by R naught into 1 plus alpha naught T2, and R1 is given by R naught into 1 plus alpha naught T1, right? So these are the two equations. So then divide one over the other, then we will get this equation automatically. R2 by R1 is equal to, okay, so R naught gets cancelled. Okay, so now from the above expression, if we divide with alpha naught, divide both up and down, we will get T2 plus 1 by alpha naught by T1 plus 1 by alpha naught. Now, For aluminum, this temperature coefficient 1 by alpha naught value is given as 228. So this is how the resistance at different temperature can be calculated. Now, a small concept we need to know is skin effect, and the next after this we have proximity effect. So, what is the skin effect? What is the skin effect? So, this is nothing but tendency of high frequency currents to flow on the surface of the conductor. Okay, skin effect means tendency of high frequency currents to flow on the surface of the conductor. That means I'm talking about only AC current. AC current. Okay, so when AC current flows through a conductor, this is what happens. The current flows the only out. Okay, on the majority of the current flows only through the surface of the conductor. Okay, there is no current on the inner space. Okay, so this is what happens with the AC currents. This that means this skin effect comes into picture with AC currents only. Okay, that means the distribution of the current is non-uniform when AC current flowing through the conductor. Okay, so this is what we can see here in the picture. If we take a conductor like this, okay, when AC current is flowing, majority of that is available only at the surface, no current at the center. So this effect is called skin effect. And factors affecting this skin effect. So before look at the factors, look at the right side. You can see when there is a DC current flow, when there is a DC current flows through the conductor, then that whole current, total current uniformly distributed over the total surface of the conductor. Okay, that means that is what it mentioned. Cross sectional area of the round conductor available for conducting DC current. That means the current is uniformly distributed over the total surface. Okay, so in that case, the resistance is called DC resistance. Next, second case, when a low frequency current is flowing. When a low frequency, first one is DC current. Okay, second thing, low frequency AC current. When a low frequency AC current is flowing through the conductor, uh, it is how the current is distributed. Okay, that means only a smaller portion, inner portion, okay, doesn't have the current. Okay, only a smaller portion. Inside the conductor, there is no current. So this is how the current, total current AC, low frequency AC current is distributed over the cross sectional area of the conductor. Next, if we look at the high frequency AC current, this is how the current flows through the conductor. That means the almost the majority of the that current is concentrated, is flowing through the surface, only through the surface. Okay, the majority of the inner side of the conductor, there is no current. Okay, this is what the meaning. This is the high frequency. This is what happens with high frequency AC. Okay, now the factors affecting skin effect are, you can see, so first factor is frequency. Okay, frequency. So here skin effect increases with the increase in frequency. Okay, so that is a first factor, frequency. If the frequency is more, skin effect also increases. It is increases. Next, diameter. Okay, this affects with diameter also. If what they're telling is the skin effect increases with the increasing diameter of the conductor. Then third one, the shape of the conductor. Skin effect is more in the solid conductors and less in the standard conductors. So we know that, okay, what is a standard conductor? Standard conductor means number of small wires are bound together to get a long conductor, large conductor. Okay, so here they're telling the skin effect is more for solid conductor than a standard conductor. Then type of material, conductor material. Okay, they're telling the skin effect increase with the increase in permeability of the material. Okay, so that is the thing they're telling, the skin effect increases with the increase in the permeability of the material. That means if good conductor materials like iron, they have good permeability value. So in that case they have the skin effect also more. Next, proximity effect. This proximity effect, okay, means what? So proximity effect means tendency for currents to flow in the on other undesirable patterns, undesirable loops due to the presence of magnetic fields produced by the neighboring conductors. Okay, so proximity effect means tendency for the current, okay, to flow in undesirable patterns due to what? Due to the magnetic field produced by nearby conductors. You can see in the picture, okay, there, first picture on the left side, there are two conductors, conductor 1 and conductor 2. Okay, so here if the currents are flowing in the same direction, okay, this is how the magnetic field. And then on the right side, if you can see the currents flowing in the opposite direction. Okay, so this is just showing two nearby conductors with different current directions. Okay, so whatever may be the current direction, there is magnetic field produced by nearby conductor. So uh, so depending upon the current direction, the magnetic field effect may be less or more, but there is magnetic field effect, okay, due to that nearby conductor. So finally, this proximity effect comes into picture. Continuation. If DC flows on the surface of the conductor, then the currents are uniform distributed around the cross-sectional area of the conductor. Hence, no proximity effect occurs on the surface of the conductor. So, the point is that telling with DC current, okay, with DC current, there is no proximity effect. Okay. Now, factors affecting the proximity effect. Now, so there are four factors. Frequency. Okay, first one, the proximity effect increases with increase in frequency. Diameter, proximity effect increases with increase in conductor diameter. And the third one, structure, means this effect is more in solid conductor than standard conductor. Example, ACSR. Okay, because surface area of the standard conductor is smaller than the solid conductor. Okay, next, fourth one, material, type of material. If the material is made up of high ferromagnetic material, then the proximity effect is also more. So now, inductance. So we entered into the calculation of inductance. So for that, first know the basic definition of inductance. So that is given like this. The voltage induced in a conductor is given by the voltage induced in a conductor is given by, okay, which is E d psi by dt. D psi by dt. Psi means flux linkages. Okay, so rate of change of flux linkages. Okay, now um, now the same expression can be written as uh, d psi by di into di by dt, means multiply and divide with di, multiply and divide with di. So now it is written as d psi by di is L, which is nothing but inductance. Okay, so inductance L into di by dt. So L is the inductance in Henry. Now, in a linear magnetic circuit, the flux linkages vary linearly with the current such that inductance remains constant. So, it is given by psi by I, psi by I. So, finally, that is a definition for inductance. Okay, so we are going to derive the expression for inductance for a single phase transmission line as well as a three phase transmission line. So to get that, this is a basic definition we need to know, okay, which is given as inductance is defined as ratio of flux linkages to the current flowing in the line, psi by I. Units of inductance are Henry. Okay, so from this psi is given by L into I. So first, a single phase transmission line, which is also called a single phase wire or single isolated current conductor. Okay, we know that a single phase line means there is only one conductor and return path is ground. Okay, so get the inductance expression for the single phase transmission line. Okay, now first point, transmission lines are composed of parallel conductors and can be assumed as infinitely long. Okay, that is a basic point. We all know that. And second point, to determine the inductance, first we develop expressions for flux linkages of isolated current carrying cylindrical conductor with written path lying at the infinity. So, to get the expression of inductance, first we have to develop the expressions for flux linkages. Okay, that is what they're telling. Next, third point, the magnetic flux lines are concentric closed circles with direction given by Fleming's right hand thumb rule. Okay, so here if you can see, if the current is flowing in a conductor through a conductor, okay, cylindrical conductor, then the internal flux is nothing but inside the conductor. External flux is the flux on the surface of the over the surface of the conductor. And this is how the right hand thumb rule to know the direction of the flux lines, magnetic flux lines. So if this is how current direction is given in the direction of thumb, then this fingers gives the direction of the magnetic flux lines. Next, a continuation. To calculate the inductance of conductor, it is necessary to consider the internal flux and external flux. So we need to first know the uh, flux linkages. Under that flux linkages, again we have two things: internal flux linkages, external flux linkages. So we first calculate those, okay, expression for internal flux and external flux. Then finally we look at the inductance expression. Now, this division is helpful as the internal flux links a smaller amount of current as we proceed towards the center of the conductor, and the external flux always links the total current inside the current. Okay, so this is what it shows. So this is a solid conductor, okay, carrying current, internal flux lines. The second figure shows, okay. So this flux, okay, internal flux links with a smaller amount of current because this is AC current. So basically we know that when AC current is flowing, majority of the current is available at the surface. So what happens to the external flux? It links with almost total current, okay, flowing through the conductor. Only a smaller current is flowing inside. So internal flux linked with the only a smaller amount of current. So flux linkages of a current carry conductor due to internal flux. So to get the expression, okay, consider a single conductor shown here, whose radius is small r. Okay, the radius of the conductor here is small r. Okay, now now consider inside the conductor, this conductor, consider a cylinder whose radius is small x. Whose radius is small x. Okay. So smaller is the radius of the conductor, and we consider this cylinder inside the conductor whose radius is x. That means this exists a distance of x meters from the center of conductor. Okay. Now we take the magnetic field intensity H. Okay. First we get the magnetic field intensity H. Okay. On the surface of this cylinder. Okay. On the surface of this cylinder. So this Hx expression is given by like this. To get the expression this Hx, okay, they're telling the MMF around a concentric closed circular path of radius x internal to the conductor is integral of H, okay, integral of Hx dl equal to Ix. Say that equation 1, okay, this is a MMF, okay. Now this field is symmetrical, so Hx is constant at all points from the center of conductor. Therefore 2 pi x into Hx is equal to Ix. Okay, so because it is symmetrical, so this is how the first equation is written as like this, and say that this is equation 2. And now neglecting skin effect and assuming uniform current density, Ix is given by, that means current at on the current at on the cylinder is given by pi x square pi r square into I, okay, where I is a total current flowing in the conductor, okay. So x square by r square. Now from these equations 2 and 3, finally this is what we want, okay. The magnetic field intensity on the on the cylinder, surface of cylinder, especially at the point considered a point x, okay. So and also we have taken x is the radius of the cylinder, or it is at a distance of x meters from the center of conductor. So it is given by, okay, I by 2 pi r square into x. I by capital I by 2 pi r square into x. So this is obtained from the equations 2 and 3, which are equated. So finally this is the expression, okay. This is what magnetic field intensity at on the surface of the cylinder at a distance of x meters. Finally, this is what, okay, we want. Now from this, the magnetic flux density P, magnetic flux density B is given by like this, okay. denoted with B, X, B suffix S. So we know that B is given by, from the basic definition, B in terms of H, B is equal to mu H. B is equal to mu H, where mu is given by mu naught into mu R. Okay, here mu R is equal to relative permeability, mu R means. Okay, so relative permeability for a conductor, it is 1. So that's why it is, okay, it is not shown here. So Bx is equal to mu naught into, okay, substituted Hx expression, I by 2 pi r square into x. Okay, now mu naught value is, okay, this is a basic knowledge. Mu naught is permeability of free space, okay, or air, whose value is 4 pi into 10 power minus 7. 4 pi into 10 power minus 7. Next continuation, the flux, okay. Here to get the flux, let us consider a small tubular element of thickness dx. Okay, so we know that here it is considered at a distance of x meter. Okay, a cylinder. Now they are telling take a tubular element of dx. So this is a dx. Okay, thickness, and the length of the conductor is, let us take 1 meter. Now the flux lines, okay, the flux in the tubular element is given by, because already we have the bx. So what is pi is given by bx into a, area, right? This is a basic expression. B is equal to flux by area. So from this knowledge, so the flux is given by, in the specific tubular element whose thickness dx, they have taken d pi x is equal to bx into, okay, a. So where a is written as, okay, what is the tubular element length? We have taken dx, and the length of the conductor is taken as 1. So it is written as that a is area of cross section of conductor is written as dx into 1. So substituted for bx, we know that mu naught I by 2 pi r square x into dx. Now after this, um, the flux linkages is given by, okay, flux linkages is given by psi, right? So, which is given by, in terms of flux, as flux into number of turns. Number of turns. Okay. So, this is what the flux linkages. This is what the flux linkages. So, finally, we are writing flux linkages as d psi, okay, d psi. So now we are writing at a point x, right, at a distance of x meters. So now the flux d pi links with only a fraction of the conductor. Now, okay, a small fraction of the conductor, d pi is nothing but, that is a flux, okay, with respect to a small part of the conductor. Now we want to write that for the total conductor. Okay, so then therefore on the assumption of uniform current density, only the fractional term pi x square with pi r square of the total current is linked by the current. So now it is written as, okay, this is nothing but d psi is equal to flux into, what is the flux here? It is a total, okay, with respect to the total conductor now. So that is nothing but x square by r square. So pi x square by pi r square. From that it is x square by r square into, okay, d pi x. So substituted for d pi x. So finally the expression is given by mu naught I by mu naught I by okay, this number of turns is 1. Okay, only one conductor we have. Okay, then flux into, with respect to the total conductor, it is written as, okay, x square, pi x square by pi r square. So that we get it like this, x square by r square. So here substitute for d pi x. So next, here to get, that is a d pi expression, d psi expression, sorry, d psi expression. So we want psi. Okay, so what we do, integrate the expression with respect to total radius of the conductor. Okay, so because we know that the radius of the conductor is smaller, so what are the integration? Okay, so if we do the integration and the limits become 0 to r. So the total internal flux linkages, okay, is given by psi, int means internal. So in mu naught I by 2 pi smaller 4 power 4 x cube dx with the integration limits 0 to r. 0 to r. So this expression is given by mu naught I by 2 pi, okay, r4 and integral of x cube dq. So integral of x cube dq becomes what? Mu naught I by 2 pi, okay, r4 integral of r x cube f dx becomes, this whole becomes, okay, x4 by 4. So if we substitute the limits, r for 4, r4 gets cancelled. So what is that we have? Mu naught by 2 by, okay, mu naught I by 2 pi into a4. So the internal flux linkages is given by mu naught I by 8 pi. Mu naught I by 8 pi. So this is the expression for internal flux linkages. Okay, if we substitute for mu naught, okay, this is the expression for psi internal. If we are interested in internal inductance, actually this is not required here, because we want to get the expression for inductance, okay, with respect to single phase transmission line. That means single phase conductor means sum of the internal flux linkages and external flux linkages. So just at this stage, this is the expression. Okay, remember, we need to remember, okay, mu naught I by 8 pi and the units for flux linkages Weber turn per meter length. So where mu naught is 4 pi into 10 power minus 7. So next, this is the internal flux linkages expression, and that's all for this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.